Look up, just for a second. Past the rooftops, past the glow of the streetlights, past the thin smear of atmosphere that keeps us breathing, past the satellites that orbit like silent watchmen. Keep going, higher, until you hit that pale, cratered sphere hanging in the black. The moon. For 53 years, it's been a museum exhibit, a monument to what we did, not what we're doing. We've sent robots there. We've crashed probes into it. We've mapped every ridge, every valley, every shadowed crater with radar and laser and orbiting eyes. But humans? Flesh and blood, heartbeat and breath, boots and gloves? No. Not since December 1972. Not since Eugene Cernan left his last footprint in the dust and climbed back into a lunar module that looked more like a tinfoil origami than a spacecraft. And then, quietly, without fanfare, without the drum roll of a Cold War arms race, the machinery of return began to turn again. Not in secret, not in whispers, but in wind tunnels, in test stands, in clean rooms, in congressional hearings, in simulation chambers where astronauts practiced walking in 1/6 gravity until their muscles memorized the rhythm. NASA didn't just announce a new mission. It resurrected a dream that had been mothballed, politicized, canceled, rewritten, and resurrected more times than anyone cared to count. It called it Artemis. And when the words finally crossed the threshold from concept to countdown, something shifted. Not just in the aerospace industry, not just in the halls of power, but in the collective nervous system of a species that had, for half a century, told itself the story of going back was just that, a story. Until it wasn't. Because here's the thing about Apollo. It wasn't sustainable. It was a sprint, a geopolitical sprint, a demonstration sprint. We went because we had to prove we could, not because we were building a foothold. We packed our experiments, planted our flags, collected our rocks, and came home. The infrastructure was left behind. The launch sites were repurposed. The blueprints were archived. The generation that built Saturn V aged into retirement, and the institutional memory of how to do it fractured into fragments. For decades, returning to the moon sounded less like a plan and more like a political placeholder. Something you say when you want to sound ambitious without committing to the cost, the risk, the decades-long grind. But Artemis isn't Apollo 2.0. It never was supposed to be. It's a different animal entirely. Where Apollo was a solo expedition, Artemis is the first brick in a foundation. Where Apollo was about leaving footprints, Artemis is about leaving equipment, habitats, power grids, and eventually, people who don't just visit, but live. The moon is no longer the destination. It's the proving ground, the training camp, the dry run for Mars. And maybe, if we're honest about where this is all heading, the first step toward becoming something other than a single planet species. But before we talk about the rockets, the suits, the orbital stations, the lunar rovers, the water ice at the poles, the international partnerships, the private contractors, the billion-dollar contracts, the engineering miracles, the life support redundancies, the radiation shielding, the navigation challenges, the dust mitigation, the communication delays, the psychological toll, the legal frameworks, the economic implications, the philosophical weight of it all. Before any of that, we have to ask the question that's been hanging in the vacuum for half a century. Why did we stop? And why, after 53 years of silence, are we finally going back? The answer isn't just technical. It isn't just political. It's human. And it's messy. And it's beautiful. And it's about to change everything. Stay with me. Because what's happening right now isn't just a mission. It's a reckoning. And it's only just beginning. Chapter 1. The silence after the footprints. Let's rewind. Not to 1969. Not to the first step. Let's rewind to 1972. December 14th. The exact moment the last human being walked on the moon. Eugene Cernan. He didn't just climb down a ladder. He backed out. He closed the hatch. He sat in the ascent stage. He fired the engine. He left behind a descent stage, a flag, a seismometer, a laser reflector, a plaque, and the quiet understanding that no one would follow him for a very, very long time. And he was right. Why? Because the political engine that drove Apollo had already burned out. The Cold War space race was effectively over. The Soviet Union had conceded defeat in the crude lunar race. The public had seen it done. 6 times. The novelty was gone. The cost was staggering. In today's dollars, Apollo consumed over $200 billion. Adjusted for inflation and economic scale, it was a wartime-level mobilization. And once the objective was met, the political will evaporated. Congress slashed funding. NASA pivoted to Earth orbit. The space shuttle program was born out of necessity, not ambition. It was designed to be reusable, routine, practical. A space truck, not a space cathedral. But here's the uncomfortable truth. The shuttle was never going to get us back to the moon. It couldn't. It was low Earth orbit only. It was brilliant for what it did, deploying satellites, building the ISS, servicing Hubble. But it was structurally incapable of translunar injection. It lacked the escape velocity. It lacked the life support duration. It lacked the radiation protection. It was a masterclass in near-Earth logistics, but a dead end for deep space. So we stayed close. We built a space station. We learned how to live in microgravity for months at a time. We mastered rendezvous and docking. We developed international partnerships that outlasted the Cold War. But we stopped going farther. The moon became a place on maps, not a place in flight, manifests. And yet, the desire never died. It just went underground. It lived in textbooks. It lived in simulation labs. It lived in the minds of engineers who grew up watching grainy footage of lunar module landings and thought, I want to build the next one. It lived in scientists who studied returned samples and realized the moon wasn't just a dead rock. It was a time capsule, a geological archive, a mirror reflecting Earth's violent infancy, a place with water, yes, water, not just in ice caps, but bound in the regolith, trapped in permanently shadowed craters, hiding in plain sight, while we spent decades assuming the lunar surface was bone dry. That discovery changed everything. Water means oxygen. Oxygen means breathable air. It also means hydrogen. Hydrogen means fuel. Fuel means you don't have to bring everything from Earth. Fuel means you can refuel in space. Fuel means the moon isn't a destination, it's a gas station. But knowledge isn't enough. You need architecture. You need policy. You need sustained funding. You need a program that survives election cycles, budget committees, shifting geopolitical priorities, and the inevitable failures that come with pushing the boundaries of what's possible. For decades, we tried and failed. Or rather, we started, stopped, restarted, rebranded, and abandoned more lunar programs than you can count on one hand. Constellation, cancelled. Space Launch System, delayed. commercial lunar payload services. Promising, but still payload only, every attempt stumbled over the same three rocks: cost, complexity, and political continuity. You can't build a lunar program in 4-year increments. You can't design a spacecraft and hope the next administration will honor the funding. You can't train astronauts for a mission that might get defunded before launch. It's like trying to build a cathedral while the mayor changes his mind every time a new council takes office. Artemis survived because it learned from those ghosts. It didn't try to do everything at once. It broke the return into phases. It embraced commercial partnerships instead of relying solely on government contractors. It leveraged the International Space Station's operational experience. It designed for sustainability, not just flags and footprints. And it built a coalition, not just with traditional space agencies, but with private companies, academic institutions, international partners, and a generation of engineers who had never seen a human launch to deep space, but had spent their entire careers preparing for it. But preparation isn't execution, and execution is where the rubber meets the vacuum. Because returning to the moon isn't about nostalgia, it's about necessity. The moon is the only place beyond Earth where we can practice living, working, and surviving in an environment that mimics the challenges of Mars, but with a 3-day emergency return window. It's where we test closed-loop life support. It's where we experiment with in-situ resource utilization. It's where we learn how to build with regolith, how to shield against solar particle events, how to navigate without GPS, how to communicate across lag, how to maintain equipment in abrasive, electrostatically charged dust that gets into everything, ruins seals, degrades optics, and laughs at your best engineering solutions. It's a classroom, a brutal, unforgiving, airless classroom. But it's ours, and we're finally ready to sit in it. But ready is a strong word. Prepared is better. Equipped is closer. But truthfully, we're stepping into the unknown with better tools, smarter systems, and harder-earned wisdom. But the moon hasn't changed. It's still airless, still radiation blasted, still covered in dust that acts like powdered glass, still subject to temperature swings that can crack steel if you're not careful, still utterly indifferent to human ambition. That's what makes Artemis so compelling. It's not a victory lap, it's a stress test. For our technology, for our institutions, for our patience, for our willingness to accept that exploration isn't linear, it's iterative, it's messy, it fails, it adapts, it tries again. And this time, we're not just going back to prove we can. We're going back to prove we can stay. Chapter 2. The ghost of a program that never was before Artemis. There were ghosts, dozens of them. Programs with names that sounded like they belonged in science fiction. Programs that made it to PowerPoint slides, to congressional briefings, to early hardware prototypes, before being quietly shelved, rebranded, or canceled outright. You don't reach 2026 without tripping over the bones of abandoned lunar ambitions. And if you want to understand why Artemis is different, you have to walk through that graveyard first. Let's start with the 1980s. After the shuttle was operational, NASA quietly drafted plans for a permanent lunar base, not a visit. A base, modules, power systems, habitats, rovers. The idea was to establish a continuous human presence by the late 1990s. It was called the Lunar Exploration Program. It had studies, It had conceptual designs. It had budget projections that made economists wince. It died in committee, not because it was impossible, because it was expensive. And expensive, in Washington, is a 4-letter word. Then came the 1990s. Post-Cold War, the Soviet Union collapsed. The space race was officially over. NASA pivoted to commercialization, to Earth observation, to the International Space Station. The moon was relegated to future consideration. Robots took the lead. Clementine mapped the surface. Lunar Prospector confirmed hydrogen signatures at the poles. The data was revolutionary. The political will was non-existent. You don't build rockets for data points. You build them for prestige, for strategy, for survival. And in the 1990s, the moon offered none of those at scale. Then came 2004. President Bush announced the vision for space exploration. Retire the shuttle, build crew exploration vehicle, return humans to the moon by 2020, establish a sustainable presence, use the moon as a stepping stone to Mars. It sounded ambitious. It sounded coherent. It sounded like a plan. It became Constellation, Orion, Ares 1, Ares 5, Lunar Module, Heavy Lift, Deep Space Habitation. It had contractors. It had timelines. It had test articles. It even had patches. And then, in 2010, it was canceled. Not because the technology was flawed, not because the astronauts objected, because the budget projections ballooned, because the technical challenges of Ares 5 proved more complex than anticipated, because the political landscape shifted, because the Augustine Commission concluded the program was unsustainable under projected funding. Canceling Constellation wasn't just a budget decision, it was a cultural rupture. Engineers who had spent years designing heat shields, flight computers, propulsion systems, launch abort mechanisms, found their work shelved. Some left the industry, some pivoted to commercial space, some stayed, hoping the next iteration would survive. And when Orion was saved from the scrap heap and repurposed for deep space, when the Space Launch System was born from the ashes of Ares, when the Lunar Gateway concept emerged from orbital logistics studies, the industry realized something. The moon wasn't off the table. It was just being rebuilt. But rebuilding isn't starting from scratch. It's carrying the weight of everything that came before. Every canceled program leaves behind institutional knowledge. Every shelved prototype teaches a lesson about materials, about thermal stress, about software architecture, about human factors in confined spaces. Artemis didn't emerge in a vacuum. It emerged from a half-century of trial, error, cancellation, revision, and quiet persistence. And that persistence took a different shape. Instead of a monolithic government program, Artemis embraced a distributed architecture. NASA sets the requirements. International partners contribute modules, logistics, science instruments. Commercial companies build landers, deliver cargo, develop habitats. Academia trains the next generation of engineers. Private investment accelerates development. It's not a single rocket, it's an ecosystem. That's the first major departure from Apollo and Constellation. Apollo was NASA doing everything. Constellation was NASA doing almost everything. Artemis is NASA orchestrating. And orchestration is harder than execution. Because you can't mandate commercial innovation. You can't legislate private sector agility. You can only incentivize it, fund it, guide it, test it, certify it. And when it fails, absorb the lesson, adjust the parameters, and try again. That's why the Commercial Lunar Payload Services program matters. It's not just about delivering experiments. It's about proving that companies can land on the moon reliably, that they can navigate, communicate, deploy power, handle dust, manage thermal cycles, and operate autonomously when Earth isn't in view. Every successful CLPS mission is a data point. Every failure is a lesson. And the accumulation of those data points is what de-risks Artemis. Because Artemis isn't betting everything on one lander. It's building a pipeline. Multiple providers, multiple designs, multiple landing strategies. Redundancy isn't just a safety feature, it's a survival strategy. In deep space, single points of failure don't just end missions, they end lives. And NASA knows that. The engineers know that. The astronauts know that. Which is why Artemis 3 isn't just a test. It's a validation of an entire operational model. But operational models don't win public imagination. Landings do, flags do, footprints do, and that's where the tension lies. Between the slow, methodical, infrastructure-heavy reality of sustainable lunar exploration and the public's expectation of cinematic, immediate, historic moments. You can't rush engineering. You can't compress testing. You can't skip failure analysis. But you also can't lose the narrative. Because narratives drive funding. Funding drives hardware. Hardware drives missions. Artemis walks that tightrope. It promises a woman and the first person of color on the moon. It promises a sustainable presence. It promises a pathway to Mars. But it also has to deliver on the technical realities: radiation exposure, life support reliability, landing precision in rugged terrain, dust mitigation, power generation during lunar night, thermal management, communication latency, emergency abort protocols, crew health monitoring, psychological support in isolated environments, and the simple, brutal fact that space doesn't care about your schedule. And yet, it's happening. Not because it's easy, because it's necessary, because the alternative is stagnation, because Earth's orbit is crowded, because low Earth orbit is becoming commercial real estate, because deep space requires deep capability. Because if we want to go to Mars, we can't launch from Earth and hope for the best. We need to stage. We need to refuel. We need to practice. We need a lunar proving ground. And the moon is waiting. Not patiently. It never has. It's waiting indifferently. And that's exactly why we have to go. Because indifference is the ultimate test. It doesn't reward ambition. It only respects preparation. Chapter 3: Why Artemis Isn't Just Apollo 2.0. Let's kill a myth right now. Artemis is not a rerun. It's not Apollo with better computers. It's not a nostalgia trip wrapped in modern avionics. It's a fundamentally different paradigm. Apollo was about going. Artemis is about staying. Apollo was a sprint. Artemis is a marathon with supply depots. Apollo brought everything it needed from Earth. Artemis plans to make what it needs on the moon. That distinction changes everything. Think about it. If your mission lasts 10 days, you can pack 10 days of oxygen, 10 days of water, 10 days of food, 10 days of power. You design for short-term survival. You accept that once you leave, you're committed. You don't plan for long-term habitation. You don't plan for resource extraction. You don't plan for infrastructure. You land, you work, you leave. The descent stage becomes a launch pad. The ascent stage goes home. The descent stage stays forever. Artemis flips that model. It's designed for duration, for rotation, for continuous presence. That means habitats, not temporary shelters. Habitable structures with radiation shielding, thermal regulation, air recycling, water recovery, waste processing, sleeping quarters, exercise equipment, medical supplies, communication arrays, and redundancy. Lots of redundancy, because in deep space, there's no quick rescue, no ambulance helicopter, no hospital on standby. If something fails, you fix it, or you survive with what's left. That's why the Lunar Gateway matters. It's not a space station for the sake of having one. It's an orbital staging point, a refueling depot, a logistics hub, a safe haven, a place where landers can dock, transfer crews, perform checks, wait for optimal landing windows, and return without having to launch from the surface directly to Earth. It changes the mission architecture from all-in-one shot to modular, phased, sustainable. And modularity changes everything, because if you can break a mission into phases, you can test each phase independently. You can fail safely. You can iterate. You don't have to risk everything on a single launch. You can send cargo first, test the lander, verify the habitat, confirm power systems, then send crew. That's not just smarter engineering, it's smarter risk management. But smarter risk management requires smarter technology, and that's where Artemis diverges sharply from Apollo. Apollo used analog computers, mechanical switches, manual navigation, limited telemetry, and ground-controlled decision loops. Artemis uses autonomous systems, AI-assisted diagnostics, real-time health monitoring, precision landing algorithms, hazard avoidance radar, terrain relative navigation, and machine learning models that can predict system failures before they happen. You can't navigate the moon's south pole with 1960s tech. The terrain is brutal, craters within craters, slopes that defy intuition, shadows that swallow sunlight for months, boulders that can flip a lander, dust that blinds sensors. You need precision. You need adaptability. You need systems that can see, think, and adjust in real time, because ground control is minutes away. And in a landing sequence, minutes are lifetimes. Artemis landers aren't just rockets. They're robotics platforms. They're autonomous vehicles. They're precision delivery systems. And they're designed to be reused, not all of them. But the concept is there. Where Apollo landers were single-use, Artemis aims for sustainable architecture, refuelable, upgradable, adaptable, because sustainability isn't a buzzword, it's an engineering requirement. And then there's the human factor. Apollo astronauts were test pilots, brilliant, courageous, highly trained, but they operated in a framework where mission control called most of the shots. Artemis astronauts are scientists, engineers, medics, technicians. They're expected to conduct field geology, deploy instruments, maintain habitats, troubleshoot life support, conduct EVA operations, manage power grids, and communicate scientific findings in real time. They're not just visitors, they're operators, residents, pioneers. That changes training, that changes selection, that changes mission design. You don't send a crew to live on the moon and expect them to just do experiments. You send them to build, to maintain, to adapt, to survive, to expand the footprint. And that requires a different kind of astronaut, not just physically resilient, mentally adaptable, technically versatile, emotionally stable under prolonged isolation, because the moon doesn't forgive. It doesn't care about your credentials. It only responds to competence. And competence in space is measured in margins. How much oxygen do you have left? How much water can you recover? How much power can you generate during lunar night? How much heat can your radiators shed? How much dust can your seals withstand before failing? How many days can your life support run on backup before critical systems degrade? These aren't theoretical questions, they're daily realities. And Artemis is designed to answer them before humans ever step on the surface. But design isn't deployment, and deployment is where theory meets reality. The moon's environment is hostile, not dramatically, not cinematically, but persistently. The vacuum is absolute, the radiation is constant, the temperature swings are violent, the dust is abrasive, electrostatically charged and impossible to fully contain. It gets into joints, it coats solar panels, it degrades optics, it compromises seals, it laughs at your best engineering solutions. Apollo dealt with it for days. Artemis has to deal with it for months, maybe years. That means new materials, new coatings, new filtration systems, new dust mitigation strategies, new habitat designs that prioritize longevity over novelty, new power systems that can survive 14 days of darkness, new thermal management that doesn't rely on Earth-like convection, new communication protocols that work around line-of-sight limitations, new navigation that doesn't depend on satellites. And all of it has to work together, seamlessly, reliably, redundantly. Because in deep space, there's no such thing as a minor failure. Degraded seal can become a leak. A leak can become a pressure drop. A pressure drop can become an emergency. An emergency can become a tragedy. And tragedy in space doesn't just end missions. It ends programs. It ends funding. It ends public trust. It ends dreams. That's why Artemis moves carefully. Why it tests relentlessly. Why it embraces failure as data. Why it doesn't rush the clock. Because the clock isn't the enemy. Complacency is. And complacency is what killed Constellation, what grounded the shuttle fleet after Columbia, what delayed Apollo one after the fire. What reminds every engineer, every astronaut, every mission director that space doesn't reward ambition. It only respects preparation, and preparation for Artemis isn't a phase. It's the foundation. Chapter 4: The Rocket That Defied Physics and Bureaucracy. Let's talk about the elephant in the launch complex, the Space Launch System. Love it, hate it, debate its cost, question its necessity, praise its power, criticize its delays, but you cannot talk about Artemis without talking about SLS. Because without it, there is no Orion. Without Orion, there is no crewed lunar flight. Without SLS, Artemis is just a PowerPoint. SLS is not a commercial rocket. It's not a reusable booster. It's not designed for daily launches. It's not optimized for cost efficiency. It's optimized for one thing: payload capacity to trans-lunar injection, heavy lift, deep space capability, uncompromising thrust, and in that regard, it succeeds spectacularly. The Block 1 configuration produces 8.8 million pounds of thrust at liftoff. That's more than the Saturn V, more than the Space Shuttle, more than any operational rocket on Earth. It can send Orion, the service module, the upper stage, and enough propellant to reach the moon and return. It's a beast, a brute, a testament to old-school aerospace engineering, meeting modern materials, science, computational fluid dynamics, and decades of rocketry evolution. But beasts are expensive, and expensive rockets draw scrutiny, especially in an era where commercial spaceflight has redefined what's possible at a fraction of the cost. SpaceX's Falcon Heavy can lift heavy payloads. Starship promises even more. Blue Origin's New Glenn is coming online. The market is shifting. Reusability is the new standard. Cost per kilogram is the new metric. And SLS, it's expendable. Every launch burns hundreds of millions in hardware. Every flight rebuilds core stages, solid rocket boosters, upper stages. It's not sustainable in a commercial sense, but it doesn't need to be. Not yet. Because SLS isn't competing with commercial rockets. It's enabling them. It's the heavy lifter that carries the crew vehicle beyond low Earth orbit. It's the certified, human-rated, government-funded assurance that Orion can reach the moon safely, reliably, and on schedule. Commercial landers can handle the descent. Commercial cargo can handle logistics. But the crew, the deep space transit, the life-critical journey from Earth orbit to lunar orbit and back, that's SLS and Orion's domain. And that domain isn't easy, because human rating a rocket isn't just about adding parachutes or abort systems. It's about redundancy. It's about fault tolerance. It's about proving that every valve, every sensor, every fuel line, every flight computer, every separation mechanism, every ignition sequence can perform flawlessly under nominal conditions, degraded conditions, and failure conditions. It's about testing until you can't test anymore, then testing again. Artemis 1 was uncrewed. It was a shakedown, a systems check, a stress test. Orion flew around the moon, tested heat shield performance, validated navigation, verified life support compatibility, confirmed radiation shielding effectiveness, and returned safely. It wasn't just a flight. It was a certification, a proof of concept, a demonstration that the architecture works. But certification isn't comfort, and comfort is what astronauts need before they strap in. Because human spaceflight isn't just engineering, it's psychology, it's trust. It's knowing that the machine beneath you has been tested, verified, validated, and cleared by people who've spent their careers ensuring nothing goes wrong. And when it does, that systems will catch it. And if they don't, that you'll have enough time, enough redundancy, enough training to survive. That's why SLS doesn't cut corners. It can't. Not with human lives on board, not with a program's credibility at stake, not with a 50-year gap in crewed lunar flight waiting to be closed. And yet, the delays, the budget overruns, the political criticism, the calls to cancel, the debates about alternatives, they're not unreasonable, they're necessary, because scrutiny keeps programs honest, because public funding demands accountability, because space exploration isn't a private venture. It's a public trust, and public trust requires transparency. But transparency doesn't equal cancellation. It requires context. And the context is this: building a new heavy lift rocket for deep space after decades of not doing it is hard. Harder than rebuilding commercial infrastructure. Harder than adapting low Earth orbit vehicles. Harder than testing uncrewed landers. Because human spaceflight has zero margin for error, and zero margin requires zero shortcuts. SLS uses heritage hardware where possible. The solid rocket boosters are derived from shuttle. The RS-25 engines are shuttle main engines upgraded. The avionics, the flight computers, the guidance systems, the thermal protection, they're all iterations of proven tech, refined, modernized, certified. That's not laziness. That's risk mitigation. In aerospace, heritage isn't a limitation. It's a foundation. You don't reinvent the wheel when you're trying to. reach the moon, you improve it, and improve it they have. The core stage is larger, the propellant load is optimized, the avionics are modernized, the testing regime is exhaustive. The launch infrastructure at Kennedy is rebuilt, upgraded, reinforced. The mobile launcher, the crawler, the tower, the fueling systems, the countdown sequences, the abort protocols, the weather constraints, the range safety procedures, all of it is new, or newly adapted, or newly integrated. And integration is where programs live or die. Because rockets aren't just machines, they're ecosystems, and ecosystems require harmony. The rocket, the launch pad, the ground systems, the flight controllers, the weather teams, the range safety officers, the medical teams, the recovery crews, the communication networks, the tracking stations, the backup systems, the emergency protocols, they all have to work together, seamlessly, precisely, on schedule. And when one element delays, the entire chain delays. That's the reality of human spaceflight. It's not a solo act, it's an orchestra. And conductors don't rush musicians. They ensure they're ready, because one missed note doesn't just ruin the performance, it ruins the mission. And Artemis isn't just launching a rocket, it's launching a program, a paradigm, a future. And futures aren't built on speed. They're built on certainty. Certainty that the heat shield won't fail, that the service module will orient correctly, that the trajectory will be precise, that the radiation shielding will hold, that the life support will maintain pressure, that the navigation will lock onto lunar orbit, that the return burn will ignite, that the re-entry corridor will be accurate, that the parachutes will deploy, that the splashdown will be safe, that the recovery will be swift. That's what SLS and Orion are proving, not just with numbers, with flight, with data, with successful missions, with incremental validation, with patience, with persistence, with the quiet understanding that going back to the moon isn't about beating a clock. It's about honoring the weight of the endeavor, and weight in spaceflight is measured in responsibility. Chapter 5. The Lunar Gateway and the Architecture of Return. Orion doesn't land on the moon, not directly. It doesn't carry a lander. It doesn't house surface habitats. It's not designed for lunar surface operations. It's a transit vehicle, a deep space crew capsule, a lifeboat, a command module. And when it reaches lunar orbit, it doesn't just hover. It docks, it connects, it integrates with something new, something unprecedented, something that changes the entire mission architecture, the Lunar Gateway. The Gateway isn't a space station in the traditional sense. It's not designed for continuous habitation. It's not meant for long-term crew rotation. It's not a laboratory for microgravity research. It's an orbital hub. Oh, staging post? A refueling depot. A logistics center. A safe haven. A place where landers can dock, where cargo can be transferred, where crews can rest before descent, where systems can be checked, where trajectories can be adjusted, where emergencies can be managed, where missions can be extended, where science can be conducted from orbit, where communication relays can be maintained, where international partners can contribute modules, where commercial vehicles can deliver payloads, where the future of deep space infrastructure can be tested, validated, and expanded. And it's small, deliberately, because size isn't the goal, function is. The Gateway is modular, built in phases, launched in segments, assembled in lunar orbit, powered by solar electric propulsion, equipped with habitation modules, logistics nodes, science airlocks, communication arrays, and docking ports for multiple vehicles. It's not meant to replace Earth. It's meant to extend it. That's the brilliance of the architecture. Instead of launching everything from Earth to the surface in one shot, you stage. You send cargo first. You establish power. You deploy navigation. You verify life support. You test communications. You confirm landing zones. Then you send crew. And when they arrive, they don't start from scratch. They step into a prepared environment, a functioning orbital hub, a verified system, a safe baseline. That changes risk. It changes cost. It changes mission duration. It changes science potential. It changes logistics. It changes everything. Because the gateway isn't just for Artemis. It's for what comes after. It's for sustained lunar presence. It's for Mars transit testing. It's for deep space habitat validation. It's for international cooperation in cislunar space. It's for commercial utilization. It's for scientific discovery. It's for technological demonstration. It's for proving that humans can operate beyond Earth orbit, safely, sustainably, and continuously. And continuous operation requires continuous support. That's why the gateway includes habitation, not luxury, not comfort, survival, radiation shielding, air recycling, water recovery, temperature control, sleep quarters, exercise equipment, medical supplies, communication relays, emergency protocols, redundant systems, fail-safes, backup power, isolation capability, quarantine space, decontamination procedures, psychological support frameworks, crew rotation schedules, logistics resupply timelines. It's not a hotel. It's a bunker with windows, and those windows look at the moon, not as a destination, as a neighbor, as a resource, as a proving ground, as a stepping stone. And stepping stones require balance. You don't leap, you place your foot, you test the surface, you shift your weight, you commit, then you move to the next. That's the gateway philosophy. Incremental, validated, sustainable, scalable. But sustainability isn't automatic. It's engineered, it's maintained, it's funded, it's prioritized, it's protected from political shifts, from budget cuts, from public apathy, from technical setbacks, from launch delays, from integration failures, from software bugs, from hardware degradation, from human error, from cosmic radiation, from micrometeoroid impacts, from thermal stress, from power fluctuations, from communication blackouts, from orbital decay, from docking misalignments, from valve leaks, from sensor drift, from computer crashes, from human fatigue. It's a lot, and it's necessary, because if the gateway fails, Artemis loses its staging point. It loses its safety net. It loses its operational flexibility. It reverts to direct descent, to single-shot missions, to higher risk, to lower sustainability, to shorter durations, to fewer science returns, to less infrastructure, to slower progress. And progress in space isn't measured in leaps. It's measured in steps. Verified, documented, replicated, expanded. That's why the gateway isn't rushed. It's built piece by piece, module by module, launch by launch, docking by docking, test by test, validation by validation, certification by certification, integration by integration, operation by operation, expansion by expansion. And every step is intentional, because intentionality is what separates exploration from exploitation, what separates discovery from deployment, what separates vision from vanity. The moon doesn't need our flags. It needs our infrastructure. It needs our systems. It needs our presence. It needs our persistence. It needs our patience. It needs our preparation. It needs our respect. And the gateway is how we deliver it. Not all at once. Not perfectly. Not without setbacks. But deliberately. Methodically. Sustainably. Scalably. Internationally. Commercially. Scientifically. Humanly. Because returning to the moon isn't about the past. It's about the future. And the future isn't built in a day. It's built in lunar orbit. One module at a time. One launch at a time. One docking at a time. One test at a time. One step at a time. And those steps are already being taken. Chapter 6. The descent vehicles that will carry us home. Orion gets you to lunar orbit. The gateway gives you a place to prepare, but neither of them gets you to the surface. For that, you need something else entirely, something designed for one purpose, to take humans from orbit and set them down gently on another world. The Human Landing System, the HLS. The vehicle that will actually put boots back on the moon. And here's the thing. It's not one vehicle, it's several, because NASA didn't bet everything on a single design. They opened the competition, they invited innovation, they embraced commercial partnerships, and they got multiple answers to the same question. How do you land humans on the moon safely, reliably, and sustainably? The first winner was SpaceX. With Starship, yes, that Starship, the same massive, fully reusable stainless steel beast that's designed to eventually carry humans to Mars. But for Artemis, it's being adapted, modified, human-rated, lunar-optimized. The version that lands on the moon won't look exactly like the Mars version. It won't have the same heat shield. It won't need the same atmospheric entry capability. But it will have something the Apollo lunar module never had: scale, capacity, volume. Because Starship HLS is enormous. We're talking about a vehicle that can deliver multiple crew members, tons of cargo, scientific equipment, habitat modules, power systems, rovers, and supplies in a single landing. It's not just a lander. It's a delivery system for an entire lunar outpost. And that changes the game completely. Apollo's lunar module could carry 2 astronauts for about 3 days. It had the interior volume of a small walk-in closet. It was cramped, utilitarian, and designed for short stays. Starship HLS, it's designed for extended operations, for multiple crew members, for bringing equipment that would have been impossible to imagine in the 1960s. It's not just an upgrade, it's a paradigm shift. But Starship isn't the only player. NASA also selected Blue Origin's team, the national team, a consortium of companies working together to build an alternative landing system. Their design is different, more traditional in some ways, more innovative in others. It uses liquid hydrogen and liquid oxygen. It's designed for reusability. It's built with sustainability in mind. And it provides redundancy. Because in human spaceflight, you don't want a single point of failure. You want options. You want backups. You want competition that drives innovation and keeps everyone honest. And then there's Dynetics, another competitor, another approach, another set of engineering solutions to the same fundamental challenge. How do you descend from lunar orbit to the surface without killing the crew? Because that's the hard part, not the landing itself, the descent, the controlled fall, the precision navigation, the hazard avoidance, the ability to see boulders, craters, slopes, and dust in real time, and adjust your trajectory accordingly. The capacity to hover, to divert, to abort if something goes wrong. the systems that keep you alive when you're minutes away from help and millions of miles from home. And the moon makes it harder, much harder, because there's no atmosphere, no air resistance, no parachutes, no gliding, no second chances if your engines fail. You're in a vacuum, falling under gravity, powered only by your thrusters, navigating by sensors, relying on software that has to be perfect because there's no margin for error. Apollo dealt with this using a descent engine that could throttle, a radar altimeter, and astronauts who could take manual control if needed. It worked, but it was risky, and risky doesn't scale. You can't build a sustainable presence on risk. You need reliability. You need predictability. You need systems that work every single time, not just most of the time. That's why modern landing systems use terrain relative navigation. Why they have hazard detection LiDAR. Why they can map the surface in real time and identify safe landing zones autonomously. Why they have multiple redundant engines, multiple redundant computers, multiple redundant sensors. Why they're tested thousands of times in simulation before they ever leave the ground. Because the moon doesn't forgive mistakes. It doesn't care about your intentions. It doesn't reward bravery. It only respects precision. And precision requires technology that didn't exist in 1969. Technology that's being developed right now. Technology that's being tested, validated, and certified as you read this. And the testing isn't just about the hardware. It's about the software, the algorithms, the decision trees, the failure modes, the abort scenarios, the contingency plans, the emergency procedures, the crew, training, the ground support, the communication protocols, the tracking systems, the weather monitoring, the range safety, the recovery operations. Every element has to work together, seamlessly, reliably. Because when you're descending to the lunar surface, there's no such thing as a minor malfunction. A sensor failure can mean you don't know your altitude. A software glitch can mean you don't avoid a boulder. An engine anomaly can mean you don't have enough thrust to hover. A communication dropout can mean you're on your own. And being on your own, 238,000 miles from Earth, is the ultimate test of human ingenuity, technological capability, and sheer determination. But determination isn't enough. You need the right tools. And the HLS is that tool. It's the bridge between orbit and surface, between preparation and execution, between ambition and achievement. And it's being built, not in secret, not in isolation, but in the open, with commercial partners, with international collaboration, with public scrutiny, with rigorous testing, with iterative development, with lessons learned from every success and every failure. Because failure isn't the enemy, complacency is. And the HLS teams know that. They know that every test, every simulation, every anomaly, every redesign brings them closer to a system that will work when it matters most. When humans are on board, when there's no turning back, when the only option is forward. And forward means landing, safely, precisely, reliably, sustainably, again and again and again. Because one landing is a mission, multiple landings are a program, continuous landings are presence, and presence is the goal. Not flags and footprints, not photo ops and press conferences, but sustained, operational, scientific, human presence on another world. That's what the HLS is designed to enable, not just for Artemis 3, not just for a handful of missions, but for decades of lunar exploration, for the infrastructure that will support it. for the science that will come from it, for the pathway to Mars that it represents. And that's why it matters. Not because it's new, not because it's innovative, not because it's commercially developed, but because it's necessary. Because you can't have a sustainable lunar presence without reliable transportation to and from the surface. You can't conduct meaningful science without the ability to deliver equipment and return samples. You can't prepare for Mars without proving you can operate on another world for extended periods. The HLS is the workhorse of Artemis, the unsung hero, the vehicle that doesn't get the glory of launch or the drama of re-entry. But without it, there is no surface operations, no geology, no sample collection, no habitat construction, no resource utilization, no long-term presence. It's the difference between visiting and living, between tourism and settlement, between exploration and expansion. And that difference is being engineered right now, in factories, in test facilities, in clean rooms, in simulation centers, in design reviews, in integration labs, in launch complexes, in lunar orbit, and soon on the surface itself, where it belongs. Chapter 7, the suits that will define a new era. You can have the best rocket in the world, the most advanced lander, the most sophisticated habitat. But if your spacesuit doesn't work, none of it matters, because eventually someone has to step outside. Someone has to walk on the surface. Someone has to collect samples, deploy instruments, maintain equipment, conduct repairs, explore terrain, and do the actual work of exploration. And they can only do that in a spacesuit. So let's talk about the suits. The next generation extra-vehicular mobility units, the XEMU, the suits that will clothe the Artemis generation, the suits that represent decades of lessons learned, technological advancement, and human factors engineering. Because suits matter more than you think. They're not just clothing, they're spacecraft. Miniature, wearable spacecraft that have to provide everything a human body needs to survive in the harshest environment imaginable. Pressure, oxygen, temperature regulation, radiation protection, micrometeoroid shielding, mobility, communication, life support, waste management, nutrition delivery, medical monitoring, emergency systems, all of it, in a package that weighs about 300 pounds on Earth, but only 50 pounds on the Moon, in a design that has to fit a wide range of body types, that has to allow for hours of work, that has to withstand abrasive dust, that has to function in extreme temperatures, that has to be reliable, maintainable, and safe. And the Apollo suits, they were miracles of 1960s engineering, absolutely. But they were also limited, designed for short EVAs, for two-person crews, for equatorial landing sites, for specific body types, for missions that lasted days, not months. Artemis requires something different, something better, something that can support a sustainable presence. So what's new? Let's start with mobility. The Apollo suits were stiff, restrictive. Astronauts described walking in them as moving through thick mud. They could bend at the waist, but not easily. They could reach forward, but not sideways. They could walk, but not run. And they definitely couldn't kneel, crouch, or perform complex tasks that required fine motor skills. The XEMU changes that. It has advanced joints, bearing systems that allow for greater range of motion, materials that flex without compromising pressure integrity, designs that let astronauts bend, reach, twist, and move in ways that were impossible in Apollo. They can kneel to collect samples. They can crouch to examine rocks. They can reach overhead to install equipment. They can work for hours without the fatigue that plagued Apollo crews. And that mobility isn't just about comfort, it's about capability. Because if you can't move effectively, you can't work effectively. And if you can't work effectively, you can't conduct meaningful science. You can't maintain complex equipment. You can't respond to emergencies. You can't explore. Then there's the fit. Apollo suits were custom made for each astronaut. Expensive, time-consuming, inflexible. If someone gained or lost weight, the suit had to be adjusted. If a new crew member joined, a new suit had to be built. The XEMU is modular, adjustable, designed to fit a wide range of body types, from the 5th percentile female to the 95th percentile male. That's not just inclusivity, that's practicality. It means you can have a smaller inventory of suits that can be configured for different crew members. It means faster turnaround, lower costs, greater flexibility. And it means that when NASA says they're sending the first woman to the moon, they're not just making a statement. They're engineering for it, designing for it, building for it. Because the suit fits. Because the systems work. Because the architecture supports it. But fit and mobility are just the beginning. Let's talk about life support. The Apollo suits had about 8 hours of oxygen, enough for a standard EVA with reserves. But they were tethered to a portable life support system, a backpack that provided oxygen, removed carbon dioxide, regulated temperature, and powered communications. The XEMU has a more advanced PLSS, more efficient, more reliable, with longer duration, with better CO2 removal, with improved thermal management, with redundant systems, with health monitoring that tracks the astronauts' vital signs in real time, with communication systems that maintain contact with the habitat and with orbit. And it's designed for the lunar South Pole. That's critical, because the South Pole is different from the Apollo landing sites. Much different. It has permanently shadowed craters, extreme temperature variations, rugged terrain, potentially valuable water ice, and scientific opportunities that didn't exist at the equator. But those permanently shadowed regions are cold, brutally cold. Minus 400 degrees Fahrenheit, colder than Pluto. And your suit has to function in that environment. It has to keep you warm when you're in shadow. It has to keep you cool when you're in sunlight. It has to manage the transition between the two. It has to prevent condensation. It has to protect against thermal stress. It has to maintain pressure integrity despite the extreme temperature swings. That's not easy. And it requires advanced materials, advanced insulation, advanced thermal control systems, advanced heaters, advanced radiators, advanced everything. And then there's the dust. Lunar dust is unlike anything on Earth. It's abrasive, sharp, electrostatically charged. It gets into everything. It degrades seals. It scratches visors. It clogs filters. It damages equipment. Apollo astronauts struggled with it. They couldn't keep it out of the suit. They tracked it into the lunar module. It caused respiratory issues. It was a constant problem. The XEMU has been designed with dust mitigation in mind. Better seals, dust-resistant materials, improved filtration, easier doffing procedures, decontamination protocols, systems that minimize dust intrusion and maximize crew safety, because dust isn't just an inconvenience, it's a hazard. And hazards have to be managed systematically, rigorously, continuously. But the suit isn't just about survival. It's about performance, about enabling astronauts to do their jobs effectively, to conduct geology, to deploy instruments, to collect samples, to maintain habitats, to explore, to discover. And that requires more than just keeping them alive. It requires giving them the tools they need, integrated into the suit itself. So the XEMU has helmet-mounted displays, augmented reality systems that overlay navigation data, procedure checklists, scientific information, and communication, feeds directly in the astronaut's field of view. It has enhanced lighting for operations in shadowed regions. It has improved cameras for documentation and situational awareness. It has voice-activated controls so astronauts can operate systems without taking their hands off their work. It has haptic feedback to confirm inputs. It has biometric monitoring to track crew health. It's not just a suit. It's a platform, a mobile workstation, a life support system, a communication hub, a scientific instrument, all wrapped into one. And it's being tested extensively, rigorously, in chambers that simulate lunar vacuum, in facilities that replicate lunar gravity, in environments that mimic lunar terrain, in scenarios that stress every system, in procedures that validate every function. Because when an astronaut steps onto the lunar surface in an XEMU, they're trusting their life to that suit. They're trusting that the pressure will hold, that the oxygen will flow, that the temperature will be regulated, that the communications will work, that the systems will perform, and that trust isn't given lightly. It's earned through testing, through validation, through redundancy, through quality, through engineering excellence. Because in space, there's no such thing as good enough. There's only perfect, or as close to perfect as human ingenuity can achieve. And the XEMU represents that achievement. Not the final word in spacesuit technology, but a major step forward, a foundation for the future, a system that will enable the work that needs to be done, the work of exploration, of discovery, of expansion, of becoming a multi-world species, one step at a time, one EVA at a time, one suit at a time. Chapter 8. The surface operations that will redefine human presence. The rocket gets you there. The lander sets you down. The suit keeps you alive outside. But what do you actually do once you're on the surface? What's the work? What's the mission? What's the purpose of being there beyond the historic moment of arrival? This is where Artemis diverges most dramatically from Apollo. Because Apollo was about demonstration, about proving capability, about planting flags and collecting samples and coming home. The missions were short. The objectives were limited. The operations were constrained by time, by technology, by design. Artemis is different. It's about presence, about sustainability, about building something that lasts, about conducting science that matters, about developing capabilities that extend beyond the moon, about preparing for Mars. And that requires a different kind of surface operations, more complex, more extensive, more ambitious, more permanent. Let's start with the basics. When Artemis astronauts arrive at the lunar South Pole, they're not just visiting for a few days. They're setting up for extended stays, missions that last weeks, eventually months. And during that time, they have work to do, lots of it. First priority, establish the outpost. Deploy the habitat. Set up power systems. Configure life support. Establish communications. Verify all systems are operational. Because before you can do science, before you can explore, before you can do anything else, you have to have a safe, functional base of operations. That habitat isn't just a tent, it's a pressurized module, a home, a laboratory, a workshop, a command center. It has sleeping quarters, a galley, a hygiene station, a medical bay, a science lab, an airlock, storage for equipment and samples, redundant systems for everything, radiation shielding, thermal control, fire suppression, emergency protocols. And setting it up isn't a one-person job. It requires multiple EVS, multiple crew members, coordinated operations, precision execution. Because you can't afford mistakes. You can't afford delays. You can't afford system failures. Once the habitat is operational, the real work begins. And that work falls into several categories. Science. Lots of science. Because the lunar South Pole is scientifically unique. It has permanently shadowed craters that haven't seen sunlight in billions of years. Craters that may contain water ice. Ice that's been preserved since the early solar system. Ice that holds clues to the history of water in the inner solar system, to the delivery of volatiles to Earth, to the potential for in situ resource utilization. And astronauts are going to collect it. Not just surface samples, core samples, deep drills, ice cores, samples from different depths, different locations, different geological contexts. They'll analyze them in the field. They'll document them meticulously. They'll preserve them for return to Earth. They'll conduct experiments that can't be done by robots, because human judgment, human dexterity, human adaptability are irreplaceable. But it's not just ice, it's geology. The moon is a geological archive, a record of the early solar system, of planetary formation, of impact history, of volcanic activity, of space, weathering, and the South Pole has unique geology, ancient crust, impact basins, volcanic deposits, tectonic features, all of it waiting to be studied. Astronauts will conduct field geology. They'll map terrain. They'll identify rock types. They'll collect samples from specific geological units. They'll document stratigraphy. They'll measure orientations. They'll take photographs. They'll make sketches. They'll record observations. They'll formulate hypotheses. They'll test them in the field, and they'll do it with tools that Apollo never had. Ground-penetrating radar, spectrometers, magnetometers, seismometers, heat flow probes, gas analyzers, microscopy systems, all of it portable, all of it designed for lunar operations, all of it integrated with the suit and habitat systems. But science isn't the only work. There's also technology demonstration, because the moon is a proving ground, a place to test systems that will be needed for Mars, for deep space, for long-duration missions. So astronauts will test in situ resource utilization, ISRU, the ability to make what you need from what's available on site, to extract water from ice, to split water into hydrogen and oxygen, to use oxygen for breathing, to use hydrogen for fuel, to make propellant on the moon, to refuel landers, to extend missions, to reduce dependence on Earth. That's not theoretical. It's being tested right now, with robotic missions, with small-scale demonstrations, with prototypes, with experiments, and soon, with astronauts operating the systems, maintaining them, troubleshooting them, optimizing them, scaling them up. Because if you want to go to Mars, you can't bring everything from Earth. It's too far, too expensive, too impractical. You have to live off the land. You have to use local resources. You have to master ISRU. And the moon is the place to learn how. Then there's habitat operations, life support maintenance, power system management, thermal control, waste processing, water recovery, air recycling, food production experiments, medical monitoring, crew health maintenance, exercise protocols, psychological support, team dynamics, conflict resolution, leadership, followership, communication, coordination, all of it. Every day, for weeks, for months. Because living on the moon isn't a vacation. It's work. Demanding work, challenging work, rewarding work. But work nonetheless, and it requires discipline, routine, procedures, checklists, training, preparation, adaptability, resilience, mental toughness, physical fitness, technical skill, scientific knowledge, operational expertise. Astronauts on Artemis missions aren't just explorers. They're scientists, engineers, technicians, medics, geologists, pilots, mechanics, electricians, plumbers, IT specialists, emergency responders, team leaders, diplomats, representatives of humanity on another world. They have to be all of those things, simultaneously, competently, reliably, and they will be, because they're being trained for it, right now, in simulations, in analogs, in laboratories, in the field, in the desert, underwater, in Antarctica, in every environment that can replicate some aspect of lunar operations. They're learning to work together, to trust each other, to support each other, to lead and follow, to make decisions under pressure, to solve problems creatively, to adapt when things go wrong, to maintain composure when systems fail, to keep working when they're tired, to stay focused when they're stressed, to communicate clearly when they're frustrated, to support each other when they're struggling. Because on the moon, there's no calling for backup. There's no sending for help. There's no quick rescue. There's only the crew, the habitat, the systems, the training, the preparation, the determination to succeed. And succeed they will. Not because it's easy, because it's hard, because it matters, because it's the next step, the necessary step, the step that leads to Mars, to the outer solar system, to a future where humanity isn't confined to one planet. But before that future, there's work to do. On the surface, in the habitat, in the labs, in the field, in the shadows, in the sunlight, in the cold, in the vacuum. Work that will redefine what it means to be present on another world. Not as visitors, not as tourists, not as temporary occupants, but as residents, as operators, as pioneers, as the first generation of lunar inhabitants. And that's the real mission of Artemis, not just to return, but to stay, to build, to explore, to discover, to prepare, to expand, to become something more than we are now, one EVA at a time, one sample at a time, one discovery at a time, one step toward the stars. Chapter 9. The international and commercial ecosystem behind Artemis. Artemis isn't a NASA-only program. It never was. It couldn't be. Not in the modern era, not with the complexity of the mission. Not with the scope of the ambition, not with the resources required, not with the geopolitical reality of the 21st century. This is a coalition effort, an international partnership, a commercial ecosystem, a distributed architecture that leverages the strengths of multiple nations, multiple companies, multiple institutions, multiple perspectives. And that's not just politically expedient, it's strategically smart. Because no single nation, no single agency, no single company can do this alone. Not sustainably, not affordably, not efficiently. not with the redundancy and resilience that's required for long-term success. So let's talk about the partners, the contributors, the stakeholders, the players who are making Artemis possible. First, the international space agencies. ESA, the European Space Agency. They're providing the European service module for Orion, the propulsion, the power, the life support, the critical systems that keep the crew alive on the journey to and from the moon. Without ESA, there is no Orion. Without Orion, there is no Artemis. But ESA's contribution doesn't stop there. They're also developing infrastructure for the lunar gateway, habitation modules, refueling systems, logistics capabilities, scientific instruments. They're investing in the long-term architecture, in the sustainability of the program, in the future of lunar exploration. Then there's JAXA, the Japan Aerospace Exploration Agency. They're contributing to the gateway, providing life support systems, environmental control, habitation capabilities. They're also developing their own lunar lander, their own surface systems, their own scientific instruments. They're not just passengers on Artemis, they're active participants, contributors, partners. CSA, the Canadian Space Agency, they're providing Canadarm3, the next generation of robotic arms for the gateway, autonomous, intelligent, capable of maintaining the station, servicing visiting vehicles, conducting repairs, supporting EVAs, and operating with minimal ground intervention. It's a critical capability, one that Canada has mastered through decades of experience with the shuttle and ISS. And Canada isn't stopping there. They're also developing lunar rovers, robotic systems that can explore the South Pole, that can access permanently shadowed craters, that can conduct science in environments too dangerous for humans, that can scout landing sites, that can deploy instruments, that can extend the reach of Artemis beyond what humans can do alone. Then there's the broader international community, the Artemis Accords, a framework for peaceful, transparent, cooperative exploration of the moon, signed by dozens of nations, committing to principles of interoperability, of scientific data sharing, of emergency assistance, of registration of space objects, of preservation of heritage sites, of sustainable resource utilization, of deconfliction of activities. It's not a treaty. It's not binding international law, but it's a statement of intent, a declaration of values, a framework for cooperation, and it's growing. More nations are signing on, more are contributing, more are participating, because Artemis isn't just an American program, it's a human endeavor, a species-level undertaking, a step forward for all of humanity. And that's reflected in the partnerships, in the contributions, in the shared goals, in the collective ambition. But it's not just international agencies, it's also commercial companies, private sector, industry, innovation, entrepreneurship, competition, market dynamics. And this is where Artemis really diverges from Apollo, because Apollo was almost entirely government-run. NASA contracted with companies? Yes. But the companies were vendors, suppliers, contractors. They built what NASA told them to build. They followed NASA specifications. They worked under NASA direction. Artemis is different. NASA sets the requirements, defines the objectives, establishes the standards, provides the funding. But the companies, they innovate, they design, they develop, they compete, they take risks, they invest their own capital, they build their own infrastructure, they create their own business models, And that changes everything, because commercial companies are driven by different incentives than government agencies. They're driven by profit, by market opportunity, by competitive advantage, by shareholder value, by growth, by innovation, by efficiency. And those incentives align with NASA's goals, because if companies can provide services more efficiently, more affordably, more reliably than government can, then NASA can do more with less. It can stretch its budget. It can accelerate its timeline. It can increase its capability. It can achieve more ambitious goals. That's the theory. And so far, it's working. Let's talk about SpaceX. They're not just building Starship HLS. They're revolutionizing access to space, reusable rockets, rapid iteration, vertical integration, in-house manufacturing, aggressive timelines, high risk tolerance, willingness to fail fast and learn faster. And it's working. Falcon 9 is the most flown orbital rocket in history. Dragon is the only commercial vehicle certified to carry humans to the ISS. Starship is being developed at a pace that would have been unimaginable a decade ago. For Artemis, SpaceX is providing the landing system, but they're also providing launch services, cargo delivery, logistics support, potentially crew transportation. They're not just a vendor, they're a partner, a stakeholder, a critical element of the architecture. Then there's Blue Origin, Jeff Bezos' company, developing New Glenn, developing Blue Moon, leading the national team for HLS, investing in infrastructure, in manufacturing, in propulsion, in long-term vision. Blue Origin isn't just competing for contracts. They're building capability, capacity, expertise. They're positioning themselves for the long game, for sustained lunar operations, for cislunar economy, for the future of space industry. And then there are the smaller companies, the startups, the innovators, the specialists, Intuitive Machines, Astrobotic, Orbit Beyond, providing lunar landing services through CLPS, Commercial Lunar Payload Services, delivering scientific instruments, technology demonstrations, precursor missions, risk reduction, pathfinding. These companies aren't building human-rated landers, not yet, but they're proving capability. They're demonstrating reliability. They're learning the lunar environment. They're developing the expertise that will be needed for larger missions. Then there's the infrastructure companies, the ones building habitats, power systems, life support, communications, navigation, robotics, in situ resource utilization, everything that's needed for sustained presence, Redwire, Sierra Space, Axiom Space, NanoRacks, and dozens of others, developing technologies, building systems, testing prototypes, qualifying hardware, preparing for deployment. And it's not just American companies, it's international companies too. European, Japanese, Canadian, Israeli, Indian, Emirati, companies from around the world, contributing, innovating, competing, collaborating. Because the lunar economy isn't going to be dominated by one nation or one company. It's going to be a global marketplace, a competitive ecosystem, a network of providers, of customers, of services, of products, of opportunities. And Artemis is laying the foundation for that economy, creating the demand, establishing the standards, validating the technologies, demonstrating the viability. But it's not just about commerce, it's also about science, about academia, about research institutions, about universities, about the scientific community. Because Artemis isn't just an engineering challenge, it's a scientific opportunity, a chance to answer fundamental questions. about the moon, about the solar system, about Earth, about life, about our place in the universe. And scientists are ready. They have instruments to deploy, experiments to conduct, samples to collect, data to analyze, hypotheses to test, discoveries to make. They're developing payloads, building instruments, writing proposals, forming teams, coordinating campaigns, planning operations. And they're not just waiting for Artemis, they're actively shaping it, providing input, defining requirements, prioritizing objectives, ensuring that the science is maximized, that the opportunities are leveraged, that the discoveries are enabled, because science matters. Not just for knowledge, not just for understanding, but for inspiration, for education, for the next generation, for the future. And Artemis is a scientific mission, as much as it's an engineering mission, as much as it's a geopolitical mission, as much as it's a commercial mission. It's all of those things, simultaneously, integrated, interconnected, interdependent. And that's its strength. Because no single perspective, no single discipline, no single sector can achieve what's needed alone. It takes collaboration, partnership, coordination, integration. It takes the best of government, of industry, of academia, of international cooperation, of commercial innovation, of scientific inquiry, of engineering excellence. And Artemis is bringing all of that together, creating an ecosystem, a community, a movement, a new era of space exploration, not driven by competition alone, but by cooperation, not by nationalism alone, but by shared ambition, not by short-term goals alone, but by long-term vision, a vision of humanity on the moon, on Mars, throughout the solar system, a vision that's being built right now by thousands of people, from dozens of nations, from hundreds of companies, from countless institutions, all working toward the same goal, all contributing to the same mission, all part of Artemis. Chapter 10: The Human Body and Mind in Lunar Isolation. We've talked about rockets, landers, suits, habitats, science, partnerships, technology, infrastructure. But we haven't talked about the most critical element of all, the humans themselves, the astronauts, the people who will actually live and work on the moon. Because sending humans to the moon isn't just an engineering challenge, it's a human challenge, a physiological challenge, a psychological challenge, a biological challenge, a medical challenge. And the moon is hostile to human life, not dramatically, not violently, but persistently, relentlessly, in ways that are subtle but significant, cumulative but serious. Let's start with radiation. On Earth, we're protected by the atmosphere, by the magnetosphere, by distance from the sun, by the bulk of the planet itself. On the moon? None of that. No atmosphere, no global magnetic field, no protection. Just you, and the radiation environment of deep space, solar particle events, galactic cosmic rays, secondary radiation from interactions with the regolith. All of it, all the time. And it adds up. Radiation damages cells. It breaks DNA. It increases cancer risk. It degrades cognitive function. It accelerates aging. It causes acute radiation sickness at high doses. And on the moon, you can't avoid it. Not completely. You can shield habitats. You can limit EVA time. You can monitor exposure. You can schedule missions during solar minimum. But you can't eliminate it. So astronauts will be exposed. More than on Earth. More than in low Earth orbit. More than on the ISS. And that exposure has consequences. Long-term consequences. Health consequences. Career consequences? NASA knows this. They're studying it, modeling it, mitigating it, developing better shielding, better monitoring, better medical countermeasures, better selection criteria, better career limits. But there's no perfect solution. Only risk management, only trade-offs, only accepting that exploration has costs. And radiation is one of them. Then there's the gravity, or rather, the lack of it. Lunar gravity is 1/6 of Earth's. That sounds great. Bouncing around like the Apollo astronauts did, effortless movement, reduced weight. But your body isn't designed for 1/6 gravity. It's designed for 1 gravity. For Earth. For the load bearing, the muscle use, the bone stress, the cardiovascular demands of Earth's gravity. And when you remove that, your body changes. Bones lose density. Muscles atrophy. Cardiovascular system deconditions. Balance systems adapt. Vision changes. Fluid shifts. We know this from the ISS, from decades of microgravity research, from astronauts who've spent months in space, from the medical data, the scans, the tests, the observations. But the moon isn't microgravity, it's partial gravity. 1/6, and we don't know exactly what that does to the human body. Not long term, not for months, not for years. Will it be enough to prevent bone loss, muscle atrophy, cardiovascular, deconditioning? Or will it be just enough to cause problems, but not enough to prevent them? We don't know. Not yet. Not until we have data. Until we have astronauts living on the moon for extended periods. Until we can study the effects, measure them, understand them, mitigate them. And that's one of the reasons we're going back. Not just to explore the moon, but to study the effects of partial gravity on human physiology, to prepare for Mars, where gravity is 1/3 of Earth's, where we'll need to live for months, maybe years. The moon is the test bed, the proving ground, the place to learn before we commit to the longer journey. But it's not just physical, it's psychological, mental, emotional, because living on the moon is isolating. You're far from home, far from family, far from Earth. You're in a confined space with the same people, day after day, week after week, month after month. You can't go outside for a walk. You can't feel the sun on your face. You can't hear birds. You can't smell rain. You can't experience nature. Not really. Not in any meaningful way. You're in a bubble, a pressurized habitat, surrounded by machines, dependent on systems, monitored constantly, evaluated continuously. And the view? Yes, you have the view. Earth in the sky, a blue marble, beautiful, inspiring, but also a reminder of how far you are, of what you've left behind, of what you're missing. And that takes a toll. Psychological toll, emotional toll, mental toll. Astronauts on the ISS experience this: isolation, confinement, separation, monotony, stress, fatigue, interpersonal tension, communication delays, sleep disruption, circadian rhythm disturbance. But the ISS is 250 miles from Earth. You can talk to family in real time. You can see Earth filling your window. You know that if something goes really wrong, you can be back in hours. On the moon, you're 238,000 miles away. Communication has a delay. Not huge, about 1.3 seconds each way, but enough to make conversation feel different. Enough to remind you that you're far away. And if something goes wrong, you're not coming home in hours. You're coming home in days. If you're lucky, if the systems work, if the weather cooperates, if the launch window aligns. That's a different kind of stress. a deeper kind of isolation, a more profound sense of distance. And NASA knows this. They're preparing for it, selecting astronauts who are psychologically resilient, who can handle isolation, who can work in teams, who can manage stress, who can maintain performance under pressure. They're training them in analogs, in Antarctica, in underwater habitats, in desert simulations, in long-duration isolation studies. They're developing countermeasures, virtual reality, communication protocols, team-building exercises, mental health support, psychological monitoring, stress management techniques. They're designing habitats with crew welfare in mind, private spaces, communal areas, windows, lighting that mimics Earth cycles, exercise equipment, recreation options, personal storage, ways to maintain connection with Earth. Because mental health isn't optional, it's critical. It's as important as physical health, as important as technical skill, as important as mission success. Because a crew that's not mentally healthy is a crew that can't perform, can't make good decisions, can't work together effectively, can't handle emergencies, can't complete the mission. And on the moon, there's no margin for error, no room for dysfunction, no tolerance for breakdown. So the psychological preparation is as rigorous as the physical preparation, as comprehensive as the technical training, as serious as the mission itself. Because humans are going to the moon, not robots, not AI, not automated systems. Humans, with all their strengths and all their vulnerabilities, with all their capabilities and all their limitations. And those humans have to be ready, physically, mentally, emotionally, psychologically, spiritually, ready for the isolation, the confinement, the distance, the stress, the workload, the responsibility, the risk, ready to represent humanity on another world, in the harshest environment we've ever attempted to inhabit. And they will be ready because they're preparing. Right now, training, studying, learning, adapting, becoming the first generation of lunar explorers, not just in body, but in mind, in spirit, in determination, in their willingness to go, to stay, to work, to discover, to push the boundaries of human capability, to prove that we can live beyond Earth, that we can thrive in the void, that we can become something more than we are now. One astronaut at a time, one mission at a time, one day at a time, on the moon. Chapter 11, The Pathway to Mars and Beyond. Let's be clear about something. The moon is not the end goal. It never was. Artemis isn't about the moon for the moon's sake. It's about the moon as a means to an end, as a stepping stone, as a proving ground, as preparation for Mars. Because Mars is the real objective, the long-term vision, the destination that has captured human imagination for centuries. The red planet, the next world, the place where humanity might establish its first permanent presence beyond Earth. But Mars is hard, much harder than the moon, farther away, more dangerous, more complex, more demanding. The moon is 3 days away. Mars is 6 to 9 months. The moon has a 3-day emergency return window. Mars has no return window. Once you go, you're committed. You're there for 18 to 24 months minimum, waiting for the next alignment, the next launch window, the next chance to come home. The moon has 1/6 gravity. Mars has 1/3. Still not Earth gravity, still not ideal, but better than the moon. Better for long-term habitation? Better for human health? Maybe. The moon has no atmosphere. Mars has an atmosphere, thin, mostly carbon dioxide, but enough to provide some radiation shielding, enough to enable aerobraking, enough to make landing more complex but also more efficient. The moon has water ice at the poles. Mars has water ice everywhere. At the poles, in the regolith, possibly as brine. More accessible, more abundant, more useful. But Mars is farther, much farther. Communication delay is 4 to 24 minutes each way, not 1.3 seconds. You can't have real-time conversations with Earth. You can't get immediate help. You can't rely on ground control. You have to be autonomous, self-sufficient, independent. And that's why we need the moon, because the moon is where we learn how to do that, how to live with delay, how to operate independently, how to maintain systems without immediate support, how to handle emergencies on your own, how to make decisions without consulting Earth, how to be self-reliant. The moon is the training ground, the test bed, the place to work out the kinks, to identify the problems, to develop the solutions, to validate the technologies, to train the crews, to build the experience. Because if we go to Mars without that preparation, we're gambling with lives, with billions of dollars, with the future of human space exploration. And we can't afford to gamble. Not with something this important. Not with something this ambitious. Not with something this consequential. So what are we learning on the moon that we'll need for Mars? First, in situ resource utilization, making what we need from what's available. Extracting water, producing oxygen, manufacturing propellant, growing food, recycling waste, closing the loop. On the moon, we're testing these technologies, validating them, scaling them up, making them reliable, making them efficient, making them sustainable. Because on Mars, we won't have a choice. We can't bring everything from Earth. It's too far, too expensive, too impractical. We have to live off the land. We have to use local resources. We have to master ISRU. And the moon is where we're learning how. Second, long-duration habitation, living in a closed environment, for weeks, for months, possibly for years. Maintaining life support, managing power, handling waste, recycling water, growing food, maintaining equipment, dealing with emergencies. On the moon, we're testing habitat systems, validating designs, identifying failure modes, developing maintenance procedures, training crews, building operational experience. Because on Mars, the habitat is your lifeline, your home, your protection, your only shelter from a hostile environment. And it has to work, reliably, continuously, for years. And the moon is where we're proving that it can. Third, surface operations, conducting EVAs, maintaining equipment, deploying instruments, collecting samples, exploring terrain, working in challenging conditions. On the moon, we're developing procedures, testing suits, validating tools, training crews, building expertise, learning what works and what doesn't. Because on Mars, the surface operations will be more complex, more demanding, more critical, and we need to be ready. And the moon is where we're getting ready. Fourth, autonomy, operating with communication delay, making decisions without ground support, handling emergencies independently, managing systems autonomously. On the moon, we're practicing this with 1.3-second delay, with increasing autonomy, with crews taking more responsibility, with less reliance on Earth. Because on Mars, with 4 to 24-minute delay, autonomy isn't optional, it's essential. It's the only way to operate. And the moon is where we're learning how. Fifth, crew selection and training, identifying the right people, preparing them for long-duration missions, for isolation, for confinement, for stress, for autonomy, for teamwork, for leadership, for problem-solving, for adaptability. On the moon, we're refining selection criteria, developing training protocols, testing countermeasures, building experience, learning what works. Because on Mars, the crew will be even more isolated, even more autonomous, even more critical to mission success. And the moon is where we're preparing them. But it's not just about learning. It's also about infrastructure, about building the systems that will enable Mars missions. Because you don't launch a Mars mission from Earth's surface. Not directly, not efficiently, not practically. You stage, you assemble, you refuel, you prepare. In orbit, in cislunar space, on the moon, and the lunar gateway. It's not just for lunar operations, it's a test bed for deep space habitation, for long-duration missions, for the systems that will be needed for Mars transit, the habitats, the life support, the power systems, the radiation shielding, the communication systems, the navigation, the autonomy, the crew operations, all of it, being tested, validated, refined, on the gateway, in lunar orbit, in deep space, because if it works there, it'll work on the way to Mars. And the moon itself, it's a potential source of resources, of propellant, of life support consumables, of materials. Water ice can be split into hydrogen and oxygen. Oxygen for breathing, hydrogen for fuel, propellant for Mars-bound vehicles. And if you can make propellant on the moon, you don't have to launch it from Earth. You can refuel in lunar orbit, reduce the mass you need to launch from Earth, make Mars missions more feasible, more affordable, more sustainable. That's the vision, that's the strategy, that's the architecture. Moon first, then Mars. Learn on the moon, build on the moon, prepare on the moon, then go to Mars. Not as a stunt, not as a flag-planting exercise, not as a short visit, but as a sustained presence, as a long-term commitment, as the next step in human expansion. Because that's what this is about. Not just exploration, not just science, not just technology, but expansion, growth, evolution, becoming a multi-planet species. And the moon is the first step, the necessary step, the step we're taking right now, with Artemis, with determination, with preparation, with vision, toward Mars, toward the stars, toward the future. Chapter 15, the cislunar economy and the rules of engagement. Space has always been a frontier, but frontiers aren't just about exploration. They're about economics, about resource allocation, about trade, about law, about the systems that govern how humans interact with new environments. And as Artemis transitions from demonstration to sustainability, a new domain is emerging. Not just lunar space, cislunar space, the region between Earth and the moon, the orbital highways, the staging zones, the logistical networks, the economic corridor that will define the next century of human expansion. And it's not a vacuum, not anymore. For decades, space was treated as a scientific preserve, a domain for government agencies, a place for flags, footprints, and data packets. But that era is ending. Cislunar space is becoming an operational environment, a commercial marketplace, a strategic asset, a regulated domain. And with that transition comes complexity. Not just technical complexity, legal complexity, economic complexity, diplomatic complexity. Because you can't have sustained human presence without rules, without standards, without frameworks for safety, interoperability, resource utilization, and conflict resolution. You can't have commercial activity without property rights, liability structures, and regulatory clarity. You can't have international cooperation without shared protocols, communication standards, and emergency response agreements. And Artemis is building that foundation, not through treaties, not through unilateral mandates, but through practical, operational frameworks. Through the Artemis Accords, through commercial contracting, through standardization bodies, through real-time coordination, through precedent. Let's talk about the Accords, because they're often misunderstood. They're not a space treaty. They're not binding international law. They're a set of principles, a declaration of intent, a framework for peaceful, transparent, cooperative exploration, signed by dozens of nations, committing to interoperability, to scientific data sharing, to emergency assistance, to registration of space objects, to preservation of heritage sites, to sustainable resource utilization, to deconfliction of activities. It's not perfect, it's not comprehensive, but it's operational, it's practical, it's being implemented right now through mission planning, through orbital traffic management, through landing site coordination, through communication frequency allocation, through safety zones, through transparency reports, because in cislunar space, there's no air traffic control, no maritime law, no established jurisdiction, just physics, just orbits, just trajectories. And if two landers aim for the same crater, if two rovers cross paths in a shadowed valley, if two communication arrays interfere with each other, there's no police force, there's no court, there's only coordination, only protocol, only mutual interest in survival. And that's why the Accords matter, not as legal doctrine, as operational necessity, as the difference between chaos and order, between conflict and cooperation, between isolated missions and a functioning ecosystem. But coordination isn't enough. You need economics, you need markets, you need incentives, you need a cislunar economy that isn't dependent on perpetual government funding, because sustainability requires self-sustaining activity, requires commercial viability, requires private investment, requires return on capital, and it's emerging, slowly, deliberately, but unmistakably. Let's talk about logistics, the most unglamorous, essential, economically viable sector of space operations. Cargo delivery, propellant, transfer, habitat resupply, equipment maintenance, waste removal, sample return. These aren't scientific endeavors. They're service industries. And service industries scale. They generate revenue. They attract investment. They build infrastructure. Commercial companies are already competing for cargo contracts, for refueling services, for communication relay networks, for navigation constellations, for debris tracking, for orbital maneuvering, for end-of-life disposal. The market is forming, the demand is real, the technology is maturing, the business models are being stress-tested, and the moon is the catalyst, because lunar operations require regular logistics, not one-off launches, continuous supply chains, predictable delivery windows, standardized interfaces, reliable providers. And that creates market stability. It attracts capital. It funds innovation. It lowers costs. It accelerates development. Then there's resource utilization, not just for exploration, for commerce. Water ice at the poles can be split into hydrogen and oxygen. Oxygen for life support, hydrogen for fuel, propellant for orbital transfer vehicles, for lunar ascent, for Mars transit, for satellite station keeping, for debris mitigation, for commercial servicing. If you can produce propellant on the moon, you change the economics of spaceflight. You reduce the mass launched from Earth. You lower costs. You increase frequency. You enable new mission architectures. You create a refueling infrastructure that supports not just NASA, but commercial operators, international partners, scientific missions, and eventually, private enterprises. That's not theoretical. It's being prototyped right now, with robotic extractors, with processing units, with storage tanks, with transfer systems, with market studies, with regulatory frameworks, with investment forecasts. The cislunar economy isn't science fiction. It's engineering economics. It's supply chain development. It's market creation. It's the foundation of sustainable space activity. And it requires law, not just principles, not just guidelines, but enforceable, predictable, transparent legal structures. Property rights for extracted resources, liability for orbital collisions, insurance for launch failures, contract enforcement for international partnerships, intellectual property protection for space-developed technologies, dispute resolution mechanisms for cross-border operations. These aren't abstract debates. They're operational requirements. Because investors won't fund ventures without legal clarity. Companies won't build infrastructure without regulatory certainty. Nations won't cooperate without predictable frameworks. Astronauts won't operate without safety standards, and the frameworks are being built through national legislation, through international coordination, through industry standards, through precedent, through practice, through the slow, deliberate work of lawyers, diplomats, engineers, and policymakers who understand that space isn't just a technical domain. It's a human one, and humans need rules. But rules aren't restrictions. They're enablers. They're the difference between Wild West chaos and structured expansion, between isolated efforts and integrated ecosystems, between short-term stunts and long-term presence. And Artemis is setting the precedent, not through declaration, through execution, through operational reality, through successful missions, through validated systems, through sustained activity. Because when you land repeatedly, when you refuel in orbit, when you maintain habitats, when you conduct commerce, when you coordinate with partners, when you follow protocols, when you resolve conflicts, when you share data, when you preserve heritage, when you utilize resources sustainably, you create norms, you establish standards, you build trust, you form an economy, you govern a domain. And that domain is cislunar space, the corridor between Earth and Moon, the staging ground for Mars, the testing bed for deep space, the first extraterrestrial economic zone, the prototype for interplanetary civilization. It's not coming. It's already here, quietly, deliberately, invisibly to most, but unmistakably to those building it. And Artemis isn't just exploring it, it's institutionalizing it, operationalizing it, commercializing it, governing it, one launch at a time, one contract at a time, one agreement at a time, one mission at a time. Because sustainability isn't just technical, it's economic, it's legal, it's diplomatic, it's human, and humans are already writing the rules, not in boardrooms, not in parliaments, not in treaties, but on the launch pad, in lunar orbit, on the surface, in the habitat, in the airlock, in the control room, where the future is being built, not with speeches, with systems, with standards, with sustainability. Chapter 16, the psychological horizon, what returning to the moon means for humanity. We've talked about rockets, landers, suits, habitats, dust, politics, economics, law, robotics, science, architecture, funding, partnerships, training, physiology, psychology, Mars preparation, cislunar infrastructure, commercial markets, legal frameworks, operational protocols. But we haven't talked about the quietest, most profound dimension of Artemis, the one that doesn't show up in budget reports or engineering schematics, the one that can't be measured in thrust or payload capacity or orbital inclination, the one that lives in the spaces between heartbeats, in the silence after engine cutoff, in the moment an astronaut looks out a viewport and sees Earth hanging in the black, the psychological horizon. Because returning to the moon isn't just a technical achievement, it's a cultural reckoning, a philosophical pivot, a mirror held up to humanity, a reminder of who we are, of what we've lost, of what we're capable of what we owe to the future. Apollo happened during the Cold War. It was framed as competition, as victory, as dominance, as proof of ideological superiority. And while it inspired millions, it also carried the weight of division, of us versus them, of winning versus losing, of flags planted in the name of nations, not species. Artemis is different, not because it's apolitical, it isn't, but because it's post-competitive, it's collaborative, it's inclusive, it's reflective. It's about continuity, not conquest. About sustainability, not supremacy. About presence, not prestige. And that changes the narrative. It changes the meaning. It changes the psychological impact. Because when the first woman steps onto the lunar surface, it won't just be a milestone for gender representation. It'll be a statement about capability, about equity, about the future of exploration, about who gets to go, about who gets to build, about who gets to dream. When the first person of color walks in 1/6 gravity, it won't just be historic, it'll be representative. It'll signal that space isn't reserved for a narrow demographic. It's open to humanity, in all its diversity, in all its complexity, in all its potential. And when the crew looks back at Earth, they won't see borders, they won't see divisions, they won't see political lines or economic disparities or ideological fractures. They'll see a sphere, fragile, finite, floating in the void, surrounded by nothing, supported by everything. And that perspective changes people. It always has. The overview effect isn't a metaphor. It's a neurological shift, a cognitive realignment, a sudden, visceral understanding of interconnectedness, of vulnerability, of responsibility, of scale. Apollo astronauts experienced it. They returned different, quieter, more reflective, more urgent about environmental stewardship, more aware of human fragility, more committed to global cooperation. Artemis astronauts will experience it too. But they won't just visit, they'll stay. They'll live with that perspective. They'll wake up to it. They'll work beside it. They'll sleep under it. They'll carry it back, not as a memory, as a lived reality. And that reality will ripple outward, into policy, into education, into culture, into daily life, into how we think about resources, about waste, about cooperation, about long-term thinking, about planetary stewardship, about our place in the cosmos. Because space exploration has always been a mirror. It reflects our ambitions, our fears, our divisions, our unity, our ingenuity, our limitations, our courage, our humility. And Artemis is reflecting something new, Not just technological capability, but psychological maturity. The understanding that we don't explore to escape Earth. We explore to understand it, to protect it, to value it, to appreciate it, to learn how to live beyond it so we can live better on it. That's the paradox of spaceflight. The farther we go, the more we appreciate home. The more we understand our fragility, the more we commit to preservation. The more we confront the void, the more we cherish connection. The more we push boundaries, the more we recognize limits. The more we expand outward, the more we turn inward. And Artemis embodies that paradox. It's not about leaving Earth behind. It's about carrying Earth forward, about taking our best selves into the unknown, about proving that we can cooperate, that we can innovate, that we can sustain, that we can adapt, that we can endure, that we can grow, not as nations, as a species. And that's why it matters. Beyond the engineering, beyond the economics, beyond the science, beyond the politics. It matters because it reminds us of what we're capable of when we align purpose with preparation, when we replace competition with collaboration, when we trade short-term gains for long-term vision, when we invest in curiosity instead of fear, when we choose exploration over isolation, when we build instead of divide, when we look up instead of down. The moon hasn't changed. It's still airless, still cratered, still indifferent, still ancient, still silent. But we've learned, we've adapted, we've iterated, we've failed, we've succeeded, we've canceled, we've restarted, we've questioned, we've persisted, we've questioned again, we've persisted again. And now we're ready. Not because it's easy, because it's necessary, because it's time, because the alternative is stagnation, because Earth's orbit is crowded, because low Earth orbit is commercial real estate, because deep space requires deep capability, because if we want to go to Mars, we can't launch from Earth and hope for the best. We need to stage, we need to refuel, we need to practice, we need a lunar proving ground. And the moon is waiting, not patiently, it never has. It's waiting indifferently, and that's exactly why we have to go. Because indifference is the ultimate test. It doesn't reward ambition, it only respects preparation. And preparation for Artemis isn't a phase, it's the foundation. It's in the clean rooms, in the test stands, in the simulation chambers, in the design reviews, in the integration labs, in the launch complexes, in the training facilities, in the policy meetings, in the commercial boardrooms, in the international summits, in the classrooms, in the laboratories, in the hearts of the engineers, the scientists, the astronauts, the technicians, the dreamers, the builders, the believers. It's in the silence before the roar. And that silence is almost over. Conclusion? The silence before the roar. There is a specific kind of silence that exists only on the launch pad at Kennedy Space Center. Not the silence of emptiness, not the silence of abandonment, but the silence of anticipation, of potential energy, of a moment suspended between past and future, between what was and what will be, between memory and mission. It's the silence before the roar, before the ignition, before the ascent, before the journey begins. And right now, that silence is building, gathering, intensifying. Because Artemis isn't a concept anymore. It's not a plan. It's not a dream. It's real. It's happening. It's imminent. The rockets are being built. The landers are being tested. The suits are being qualified. The habitats are being designed. The crews are being trained. The partnerships are being forged. The infrastructure is being assembled. The robots are scouting. The data is flowing. The systems are certifying. The protocols are locking in, piece by piece, system by system, test by test, launch by launch. Artemis 1 flew, uncrewed, successful, validated the architecture, proved the concept, demonstrated capability. Artemis 2 will fly, crewed, around the moon, back to Earth. No landing, but humans in deep space for the first time in over 50 years. And Artemis 3, that's the one. The landing, the return, the woman, the person of color, the new generation, the new era. It's coming. Not maybe, not if, but when. And after that, Artemis 4, Artemis 5, Artemis 6, the gateway, the outpost, the sustained presence, the rotations, the science, the exploration, the discovery, the logistics, the commerce, the infrastructure, the economy, the norms, the standards, the future, years of missions, decades of operations, generations of explorers, building toward Mars, toward the outer solar system, toward a future we can barely imagine. But it starts here, starts now, starts with Artemis, with the return to the moon, not for flags and footprints, not for Cold War prestige, not for short-term glory, but for presence, for sustainability, for science, for preparation, for expansion, for the future of humanity. Because we're not meant to stay on one planet. We're explorers, wanderers, seekers. We're driven to push boundaries, to ask questions, to seek answers, to go farther, to see more, to understand better, to build longer, to stay stronger, to live wider. And the moon is the next step, the necessary step, the step that leads to everything else. So when you look up at the moon tonight, remember this. It won't be empty much longer. Not for long, not anymore. Soon there will be lights on the surface, habitats, power systems, rovers, astronauts, activity, presence, humanity, returning to where we left off, picking up the thread, continuing the journey. And this time, we're not leaving. This time, we're staying. This time, we're building. This time, we're preparing for Mars. This time, we're becoming something more. The silence on the launch pad is almost over. The roar is coming, the ignition, the ascent, the journey. And when it comes, when those engines light, when that rocket lifts, when those astronauts depart, know this. You're witnessing history, not the history of what was, but the history of what will be. The beginning of humanity's expansion beyond Earth, the start of our future as a multi-world species, the first chapter of a story that will span centuries. Artemis is coming, and with it, the future. Look up. The moon is waiting, and we're finally ready to answer the call.